Thank you very much for the introduction, and I would also like to thank the organizers for giving me an occasion to present this work. So let me first mention that most of what I'm going to talk about today is joint work with Belinsky, Sharban-Belinsky, and Ion Nekita. And before I start to speak about free compression of free compression norms, let me start with some motivation somehow, and our motivation, since well, actually, I thought that some things would have been mentioned about that, but time was kind of short. The motivation is about the non-additivity. So it's revisiting non-additivity results for the minimum output entropy. So, well, I guess everybody knows what the problem is and why we care about it. So I'm not going to spend too much time on it, but just to set the definition. So the problem somehow is to find phi which goes, let's say, from so phi, which is a first quantum channel, and another one which I'm going to call, let's say, phi prime, which goes from m prime of C to mk prime of C, to two quantum channels, such that the minimum output entropy of phi times phi prime is strictly less than h min of phi plus h min of phi prime, where, so just to have it written somewhere, h min of phi, this is the minimum over all states, which I'm going to write like this, of the von Neumann entropy of phi of x. And so as everybody knows, this I mean, there has been lots of activity around this problem until 2007 or 2008, and the negative answer was given by Hastings, with lots of clarification afterwards by many people. I'm going to mention some works while speaking further about that. But let me first recall quickly. I mean, in all this, the ultimate proof of the fact that there exists such quantum channels. The strategy somehow was always the same, and I would like to recall here what was the strategy for finding such phi and phi prime to motivate our revisiting of the problem. So, well, the first idea probably was to, I mean, everything comes in the order that one wants somehow, because we just have to put the elements together, but somehow it was to take the same n equals n prime, k equals k prime, and to take that the second channel would be the conjugate of the first one. So this is the conjugate channel, and by conjugate what I mean is, well, let me just say, so somehow the the big problem is to find nice phi. So phi for me is going to look like this. So this is going to be it's going to be defined by phi of x. This is u x u star, and then I'm going to take a partial trace. So where u is an isometry which sends Cn in C k tens C capital N. So we should find some nice phi which has this which can always be written like that thanks to Stein-Spring theorem. And then there is a very important, a crucial observation somehow. I guess originally by maybe Werner and Winter, that so there is this lemma somehow. So I hope I'm giving the right credit, but we'll see. That if so let T be the relative dimension of this space in this bigger space. So T, this is n divided by k times n, and then what we have is that phi times phi conjugate of the Bell state. Its largest eigenvalue is at least t. So this gives an upper bound for h min of phi times phi bar, and well, then I should say somehow. Not sure. Once again, the order is kind of random here. What we have is that with this choice of phi equals phi bar, where I should perhaps have said in this setup that by phi bar I mean that I take the entry-wise conjugate of u. We have h min of phi equals h min of phi conjugate. So if I have a good bound here, and if I can find a nice estimate for this, then in principle the problem can be solved. So the purpose for of today's talk somehow is not to change this strategy. The strategy is extremely brilliant, and I think nobody has ever been able to propose another approach, namely take something different than phi conjugate for the second channel, take something different than the Bell state here. I mean, there has been some attempts. We have made some attempts, but which were unfruitful. So the problem somehow is this is where I want to focus. All the remainder this remains unchanged, and this is strategy is very well explained, for example, in the papers of Haydn and Winter. So what we want to do somehow, all the phis that so the crucial idea, well, one crucial idea somehow is that it's very difficult to find such a phi. So take phi at random. And then try to, if we take phi at random, it means that I have a probability measure on the collection of quantum channels, and then this becomes a real valued random variable, and well, the general idea is that this random variable concentrates, and if it concentrates where it should, I mean, if it concentrates in a good location, then with high probability, maybe we'll get the result. So somehow, so far, all the proofs that were given, all the examples that were given of non-additive quantum channels, I mean of quantum channels that will yield the violation of the additivity of the minimum output entropy, they were always relying heavily on the study of the real valued random variable h min of phi. And what I would like to do somehow is today to go a little bit beyond this framework. And so what we want to do, so instead we want to study the random set phi of Dn. So if you prefer, this is the collection of outputs. So I can think of it, in other words, as this is a random. Well, here actually this is a random convex subset of the density, the k by k density matrices. So I want to replace this this nice problem by a more complicated problem. But of course, so first of all, there is an obvious relation between these two problems, because if I call this set here kn, well, we have of course that h min of phi. This is the min for x belonging to kn of h of x. So somehow, if I'm able to study this set, then I will be able to study the minimum output entropy, and I will actually be able to study in the same time all the, let's say, all the Rényi minimum output entropies, for example, or any quantity which depends on the output set. So actually, we want to do a little bit more for the purpose of understanding a little bit better the mathematical properties of quantum channels, the typical mathematical properties of quantum channels that yield the violation of the minimum output entropy. Let me call this guy k tilde n, and I'm going to look at this one as well, kn, which is phi of dn pure. So the collection of pure states. This is the images of pure states. So here I have a random compact convex set, and here I have a random compact set. And in principle, there is no reason why we should expect this to have any extra structure, because it's the collection of extremal points. Apply a linear map, so why would I put anything like compact or anything like that in principle? So this looks like a more general problem. Here there was something which was very nice. So yes, something else which I should mention also is, well, instead of studying phi, we study a sequence of phis. Somehow we are now in some kind of probabilistic paradigm where we would like to obtain a limit theorem, to obtain a behavior at infinity. So we need to let some parameter go to infinity and see what happens. So here the situation was quite nice, because when we have a sequence, then it's always the same kind of a real valued random variable. So the random variables to be studied here, they all lived in the same space. Here, well, this is random sets. So here somehow it's natural to require for the parameters to have. So in our study, we fix k, and we let. So the parameter that goes to infinity is n. And actually, what I'm also going to do, because remember that this is how I am defining my sets through a Stein-Spring representation, my channel through Stein-Spring representation. We need also to explain what is the ancilla space capital N. Actually, what we have is that n is going to be a function of little n, which has the property that the limit, as n goes to infinity, of n divided by k n goes to t. So somehow t is the asymptotic relative dimension. So t is in principle a number which belongs to, let's say, I'm going to open the set even though I don't need to do that. So t is going to be a parameter which belongs to 0, 1. So I have two parameters in my study. I have k, which is the output dimension, and I have a relative dimension between states, but between vector spaces. The only thing which I did not precise at this point is which kind of randomness do I have. I have actually the only a natural randomness here, which is the random. So the random. So let me write like this. So what is the distribution? The probability distribution. The probability distribution of phi, which I'm going to call phi n. Well, it's obtained by taking u, so which is the requires the embedding from Cn to Ck times Cn at random. And by at random here, the collection of embeddings of a Hilbert space in another Hilbert space is a compact manifold. There exists a unique invariant probability measure, which is the push forward of the Haar measure by taking the first n column in a k capital N by k capital N random unitary matrix. So at random, with respect to the uniform measure. And now we have, given two parameters k and t, we have a random sequence of quantum channels which goes from mn to mk. And what I would like to do is I would like to study this random set or this random set. So now I have a very well defined problem. I'm going to focus on this problem because this is just the convex hull of that problem. So let me. So very soon, in a few minutes, there will be some relation with the lectures that we had this morning in free probability theory and in random matrices. But first, let me tell what we can obtain with this setup. So the theorem, first thing that we can obtain is that there exists a convex compact subset K of dk such that with probability 1 as n goes to infinity, my random set Kn, so the collection of images of pure states, converges towards K. So what does it mean to converge for sets? There is the collection of compact subsets of a complete metric space is also a metric space, which is endowed with the Hausdorff distance. So this converges here in the sense of the Hausdorff how do you tell whether two sets are far away from each other? You enlarge a little bit one, and you see how much you have to enlarge it so that it's contained in the other one, and conversely. This gives a distance, and in this distance, this set tends to K. And we actually have more, even though it's some kind of curiosity. Let me state it. We actually have that the boundary of this set converges to the boundary of this set too. So it's some kind of, you could think of it by saying that somehow even the first order derivative somehow converges. But more precisely, what does it mean? It means that so here K, and I'm going to define for you K in a few minutes. But for now, let's just assume that there exists such a K. So you see, we have this Kn, which is the image under a linear map of a collection of extremal points. And first of all, this highly non-convex set somehow converges to a convex set in quite a strong sense. In the sense that somehow if K is my convex set, then if I write some epsilon bold there, somehow it's contained there already. But that even tells more somehow. That tells that you could not have some kind of cheese situation where you would have some small holes in Kn that become very small, and that would still allow this to be satisfied, but that not to be satisfied. So somehow, even in the interior of K, everything is being filled within a finite amount of time. So if I restate it from the point of view of quantum channels, it means that any point that I take here in the interior of my convex of my convex body K, I can find for L large enough a pure state that will exactly land here, not approximately, that exactly lands here for L large enough, which is, it's still kind of counterintuitive as far as I'm concerned, but this is that's how it is. So of course, like I said before, this is going to help us sort this problem out here. Yeah, so the corollary of this is that H min with probability 1, the minimum output entropy of phi n converges towards the minimum for x belonging to k of hx. And well, this is already interesting to see that we have a convergence, because if you look at all the proofs that were available before, this was some upper bounds and lower bounds. So now we know exactly that there is a convergence. But the interesting thing somehow is that we can actually figure out what this minimizer is. So this is the next theorem. The minimizer of the von Neumann entropy on K is characterized, is attained at a point x whose eigenvalues are A strictly greater than B and so the point here which attains the minimum of the entropy is a point which I can fully characterize by saying it belongs to the boundary of K, and it has only two kinds of eigenvalues. It has one eigenvalue which is larger than all the other ones which are the same. So here I have K minus 1, identical eigenvalues. So actually the minimizer is not attained at only one point, but at many points, at a whole collection of points which have this this property. And here is a corollary of this. Well, so very soon the second part of my time will be devoted to explaining how K looks like, and there I will rely on the previous talks. But just believe me for now that we can make at least a few computations on this convex body K, and we can compute exactly what the value of K of X is. And the corollary is that so with so with strategy as so what did I had? I had 1, 3, 4 as described here. So without touching of this part of the proof, but just making a good choice of quantum of random quantum channel as explained here. One obtains a violation for the choice of phi n for n large enough, if and only if K is bigger than 183. So if you are below 183, you just look at these lemmas. You just compute the minimum output entropy. You look at the difference. Then you run a search over all possibilities between 0 and 1. You ask Mathematica to help you a little bit, probably. And then you see that until 182, no violation. And after 183, with probability 1, there is a violation. So this is really an if and only if. So here I want to clarify right away that it does not mean that there is no violation of additivity for K for an output of dimension less than 182. It just means that with all the techniques of proofs that we have at hand, there is none. So it means that there is no violation with a Bell state and the conjugate stuff.
You mean as n goes to infinity?
Yes. So so here the probability, I'm reasoning in some probabilistic way. So I'm having a big space, a huge space. I don't even really care about how this probability space looks like, but it's a big probability space on which my sequence of random variables live. So it's not for so this result is not going to give me an estimate for a given n. It tells me, let me pick one sequence at random, and I know that the marginal, so the low here has this property. Then with probability 1 on the collection of probability measures, I have this property. So impossible at this point to say which n. And the second thing, so again here we should ask Mathematica for some help. It's possible. So h min of phi n plus h min of phi bar n minus so h min of phi minus h of phi n times phi n bar of the Bell state can get as close as desired 2 minus log 2 for appropriate. Choice of k t. So we have actually quite a large violation in some sense. Just to compare, so I think Moto told me today that with the proofs which were available so far, maybe the bounds were something like 50,000 here, something like that, and here I don't remember, but this was 10 to the minus something for the defects of additivity. So here we can go as far as close as we want to log 2. It's still not unbounded, but it's a meaningful number, which is not too small, perhaps. And how do we do this? By the way, how do we get this? By the way, we get this by taking k goes to infinity, and t goes to 1/2. T equals 1/2 actually. So here also, it's interesting to see that a large violation will be achieved when the space when the small space here is approximately half the dimension of the product space. Okay. So well, after telling all that, I think that I have to explain you what is K, and somehow once we understand K, maybe these results will make a little bit more sense.
Is there a proof that with these kind of techniques cannot go beyond log 2?
Well, once again, for this quantity, maybe with high probability, but you see, the thing is that I guess what we really would like to have is an h min here, and there is no way. I mean, we can't rule out the possibility that if I put h min, it becomes much smaller for some reason that we don't yet understand somehow. So we are stuck somehow with this still beautiful idea of taking phi bar, and there is still nothing we can do about that at this point. Okay, so well, definition. So how to define K. So K is So K is actually something which depends on these two parameters. So for this, I would like to introduce a quantity which I call the T norm definition. So on which we call the T norm on mk of C. So by definition, so T again is a parameter between 0 and 1. So let's x belongs to mk C. So its T norm is the following quantity: p xp, where p is a projection of trace T of, let me call it a relative trace, trace T free of x. So here we heavily rely on what Ian told us this morning. What we have is an element, a random variable in a non-commutative priority space. This non-commutative priority space contains, in particular, this small finite dimensional algebra. And in the big non-commutative priority space, I have an extra p, which is a projection whose normalized trace is t, this number between 0 and 1. And I assume that these guys are free. Then, following what Ian said this morning, we can compute in principle the norm, and this is this quantity. So at this point, actually, so of course, I mean, with I'm going to tell a bit more about it, but in principle, the definition has somehow been supplied. So at this point, what we have is that this is a non-negative real number. There is nothing more we can say about it. Well, so the first fact is that this is indeed a norm, and that can also be checked thanks to Ian's lecture of this morning. And let me explain a way to understand this norm, some kind of way to understand this norm, and then there will be a relation with John Keating's lecture. So another way to understand this norm, and other way to understand the T norm is the following. So just to explain where I am in the talk at this point, I'm trying to define K. So I'm just defining at this point an important notion, which is my free compression norm, by the way, of the free compression norm of my title, which will be somehow the tool which I need to define this limiting convex body. So how to understand this? Well, let's big P be a random projection of rank little n in mk of C times m n of C. Somehow, it's not an accident. It really has a relation with what's happening here. So in this Kn by Kn matrix space, I take a random self-adjoint projection. So here again, taking a random projection is something which is very well defined. What you could do is you could take any projection, and then you could randomly rotate it. And then the distribution would be that of a random projection. And now let's look at this guy here, P x tends 1n P. So x is the guy whose T norm I'm trying to understand. I am implying it in such a way that it does not belong there anymore, but it belongs there. And what I'm doing is I'm cutting it in a random way. So this is a random matrix. This guy here is a random matrix. In, well, M and K. And K. Oh, sorry, capital N, K, capital N, K. And it turns out, so here this is actually a theorem. It's quite hard to prove it. It turns out, that the operator norm of it. So if x were self-adjoint, this would be the largest eigenvalue, the absolute value, converges with probability 1 as n goes to infinity towards f of x. So that's what is f of x. F of x is xt. That's a way to understand the T norm in a very concrete manner somehow. I mean, all this you can simulate it with MATLAB or anything like that.
Where does T come in?
T? T, so it's the same as that one here, and it relies, so T is introduced here. So this is, oh, sorry, here, like there. So P, so here again.
Oh, sorry, right, yeah. Okay.
No, I should have said that. N behaves like T N K. And actually, and you see, to make my statement completely rigorous, I should say, once again, I choose a sequence here, little n, which depends of capital N, and let the whole stuff go to infinity, and then the statement here is correct. So that's this result was also in the self-adjoint case. It was proved by Ion Sherban and me, and in the general case, it was proved by Camille Mal and me in another paper. So anyway, that's how we can understand this norm. And let me maybe explain. Where should I erase? Here maybe. So let me give the definition of K, finally. So K, this is the collection of states, of density matrices, such that for all density matrix, we have that the trace of AB is less than the T norm of B. That's the definition of K, of the K which we use in the theorem which I just erased, which we use there, and so on and so forth. So this is how it is defined. So very obviously now it's a convex body, because it's defined as an uncountable intersection of half planes. Okay. And there is actually a conceptual way think of this? Somehow what we could say is that, so it's a remark maybe, could write it like this, we could say that K is actually, well, let's look at the one ball, at the ball of center 0 and radius 1 with respect to the T norm. Let's look at the dual of this ball and intersect it with and look at the intersection with states. This is actually the definition of K. So K is somehow the dual. It's up to some appropriate slicing to have the right trace. This is the dual of this T norm on which I spent quite a bit of time. So perhaps I should say a little bit more about what K and what the T norm looks like. Because maybe this will help me to explain a bit why this result is true. So, okay, so some facts again. So let X be an element, the density matrix again. If T is larger or equal than 1 minus 1 over K, we have that the T norm of X is actually the operator norm of X. So if we look at the definition with asymptotic freeness and so on, it's not completely obvious. But if we look at the definition here, it's quite obvious. Because what we do is, let's look at the eigenspace of the largest eigenvalue. It has relative dimension at least 1 over K. And I am intersecting with a space. It's just a fundamental theorem of linear algebra. I'm intersecting two vector spaces, and the sum of the two vector spaces which I'm intersecting is more than the initial space. So the intersection has to be non-empty. And in particular, the norm has to be the operator norm. And the second observation, which is less obvious, so if T decays to 0, then the T norm decays to actually the 1 norm. This requires a little bit more of work to prove. And actually, it's not continuous at 0, because at 0, the value is 0. So it's, if I tend to 0, then it decays. This is the 1 norm. So I could write it like this. This is the x1, sorry. So this is x. I could write it as x0 plus somehow, but it's not x0. X0 is 0, or it's not the norm. So we have this thing, and somehow it's interesting to see that the problem that we somehow, so we have a new family of norm which interpolates the L1 and L infinity norm, at least on the collection of positive states. And the way we prove our results is by saying that the minimum output entropy can actually be approximated by the Rényi entropies as P goes to 0. So somehow, in some sense, in some quite precise sense, we are comparing these two families of interpolations of norms. And if we make this the comparison, we obtain the results that we want. So let me. I guess I have 10 more minutes, and let me just try to explain a little bit how the proofs of the theorems work now. Any questions? I think I should first tell something, even though I had not planned to do it in the beginning and it's not in my abstract. I should first tell a little bit why the random set Kn converges to K. So what I'm going to do is I'm going to prove a toy example, which is the somehow some yeah, whatever toy example. What I'm going to prove is that if T is strictly less than 1 minus 1 over K, you see again looks quite like that, then what I called U, which I could perhaps have called UN, so U of Cn anyway. Okay, I should put an N here, doesn't matter too much. So UN of Cn, which I'm going to call for the purpose of the explanation here Vn, included, which is a subspace of Ck tens Cn, has no non-trivial tensor in it with probability 1 as n goes to infinity. So what am I doing? I have again my little n and my capital N, which go to infinity. I choose a random subspace of this. And what I would like to explain is that if I take a random subspace, if I take any element in this space which has been chosen as random, it will not have the form A tens B, unless it's 0, of course. So in other words, it's entangled, if you prefer. And this is going to be equivalent to showing that the pure states are not contained in my limiting convexity. So I'm just telling you how to exclude some points. I'm just telling you how to exclude a very small portion of points, but actually this technique, if I manage to explain it, then you will see that it can be generalized quite a bit. So let's instead of giving a formal proof, which would maybe not be too informative, let me stick to ideas somehow. Okay. Let's try to see what happens if, on the contrary, it doesn't look rigorous what I'm saying, but you will see it can be made rigorous. So on the contrary, if we had t greater than 1 minus, let's take it strictly greater for the purpose of the explanation here, 1 minus 1 over k, then for all a in Ck which is non-zero, we would have that the intersection of Vn with A tens C capital N would not be the zero vector space, again by linear algebra, by elementary linear algebra, which means that there exists B in Cn such that, which is non-zero, such that Vn contains A tens B. So it's even worse than that somehow. The situation is even worse. If T is too big, then I don't only have separable states, but I have separable states with any choice I want for A. So it's and this actually is equivalent to having, so this statement here, like I wrote before, this is equivalent to having the projection on Vn times the projection on A times 1n projection on Vn. It's product of three guys who are of norm less than 1, so it's at most 1. It's equivalent to have actually it to be exactly 1. So there is somebody in the intersection of the images. Well, what happens, conversely, if t is strictly less than 1 minus 1 over k? In this case, we know, like I said, when I explained how to understand the t norm, that this quantity converges towards the t norm of A, which turns out to be strictly less than 1. So it means that with probability 1, for n large enough, this quantity is strictly less than 1. This is true for a given A. Now, instead of taking 1A, why don't I take 1 million A's? And I try to spread them quite well around the unit ball of CK. And I'm asking for each of these 1 million guys to have this nice behavior with probability 1. Fortunately, an intersecting 1 million times something of probability 1 is a gain of probability 1. And then I use some continuity and some net argument, and I can prove somehow the contrary thanks to this probabilistic argument. So somehow the almost sure convergence in norm allows to, plus an epsilon net argument, allows to make the converse of this rigorous argument. And then if we want exactly to understand what's going on in the general K setup, then we should not only take a rank 1 projection on K. Here, taking this guy here amounted to taking the rank 1 projection on K, but I would have to take any state and see what this means in terms of inequality. And this actually pretty much means these kind of things here. So, well, what I'm going to do, I'm going to take 2 or 3 more minutes if possible, and I'm going to draw some pictures. Okay. So I'm going to draw some pictures of K. I'm going to draw some pictures of K for K equals 3. Actually, I'm going not to draw a picture of K, it's too difficult. But I'm going to draw a picture of K intersection diagonal. I mean, if I can do it, of course, I can understand it fully because there is this unitary invariance in this problem. So here I have to intersect to look at the diagonal states. So this turns out to be a simplex triangle. And I'm going to draw 3 regimes. So you see, I could say that this is the point 1, 0, 0, the point 0, 1, 0, this is the point 0, 0, 1. So here I'm going to have the setup where t is less than 1/3. Here I'm going to have the setup where t belongs to 1/3, 2/3. And as you already know, if t is more than 2/3, then it's the L infinity norm. So the dual is the L1 norm, and then I have the whole stuff here. So this is how my convex bodies look, and then somehow to find the maximum, I'm not going to enter in details. Well, there is we have to explain a representation of K. I mean, another nice way to represent k as the image under some gradient. I'm not going to explain that. But then somehow we have to show that that any point. So by the way, where are the maximum? The maximums are here in this picture. The maximum for all LP norms, they are here. So the points A, B, 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 which I was describing. And what we have to do is we have to show that whenever I'm in the interior, I can find an ascent direction. And well, then there are some technicalities. We have to somehow rule out a finite number of points. Still a fair amount of computations left, but anyway, that's how it works. And I better stop here, I think. So thank you very much.
So I think change the battery in the microphone. In the meantime,